Okay, we're gonna continue on here. Still, chapter 14, our favorite chapter ever. All right. We are buffering all day today. Buffers. Last time we were still talking about buffers, and we got into some buffer calculations. And remember, pretty much if it is a buffer situation, you could always use the Henderson-Hasselbalch equation, and that really is sort of what it's for, is a buffer situation. Um, Also, a reminder, as we talked about, you should not use it in every situation. It does has to be a buffer. It does has to be really a common ion, which is a buffer situation. If it is not that situation, you definitely should not use a Henderson-Hasselbalch. We also talked about that you could still, again, do an ice table if you wanted to instead of the Henderson-Hasselbalch equation. And you could either do it as like a weak acid ice table or even like a weak base ice table if you wanted to as well. The key on that, as we've been talking about, is you need to have initial concentrations on both sides to have your buffer really representative. Um, Now, something that we talked about, as we have a buffer and we add acid or base to it, much like what you did today in lab, we are changing the volume. And again, when you change the volume, the molarity of a substance does change because the liters of solution continuously changes or does change. So the difference is when we're doing sort of a calculation involving a buffer to which we have added either acid or base to it, we still need to do an ice table. And again, the purpose of the ice table is to figure out sort of what happens to your buffer, it's sort of components. And we need to do that ice table in moles. And again, the moles remain constant. And as we talked about last time, that essentially is sort of what is acting as the buffer for you, is the moles of the acid part of your buffer and the moles of the base part of your buffer that's in the beaker together to begin with. Now, as we talked about, typically you'll have the kind of first ice table here that you will do in moles, and it's a really good just habit to get into. After the first ice table in moles, you should convert back to molarity using the total volume. In the case of a buffer, the total volume would be obviously the volume of your buffer plus the volume of whatever you added in to it, either the acid or the base. Also different in this ice table than the ones that we've done previously. We do kind of know the change that should occur in this case, and we don't use X, so we actually use the moles. In most cases, you would use the moles of either the acid or base you're adding to your buffer, unless you add too much, and then you would use actually the moles of your buffer that would be used in that case. But we kind of looked at an example of that last time as well. You always want to, in that situation when you're choosing a number on the change part, as simple as it sounds, you always want to take the smaller number, right? So you don't get the negative number when you go through it and stuff like that. So, any questions on any of that there? So we're in the middle of an example which you all did at home before you came back, but maybe you did. I don't know. But let's go through it just to see how you did. I think I gave you KB on this one. I think, did I not? I gave you a KB of like 1.8 times 10 to the minus 5, I think, right? All right, I'll remember. All right, so we have basically an ammonium chloride buffer, which maybe some of you did actually make in lab today. So that was a choice of one of our lists. And we're looking for really what is the pH of the buffer before we do anything to it, after we make it. We also want to know what is the pH of that buffer after we add 20 milliliters of 0.05 molar sodium hydroxide to it. And I think I did an add-on of adding a third thing of, I want to say 2 mils of 6 molar HCl. How'd I do? Yeah, so I'm about right. That's good because I erased it, obviously. Don't have it. Thank you. All right, so let's just start with first off the buffer itself. So in this particular case, before we do anything, we're definitely not adding any volume or anything like that. So we could actually just use the molarities of our buffer components, and we could go right into the Henderson-Hasselbalch equation. Once again, here we do have a KB, which we want a pKa value for. So we can switch it, and we could get a Ka value by taking Kw divided by my Kb. This would be 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5 That's going to give me the 5.6 to the minus 10. And now I could calculate my pKa from that minus the log of 5.6 times 10 to the minus 10 in this case. That's going to give me a pKa value of 9.25. I had 5 in my head, but wrote 6, probably because I was thinking about the next thing I was going to say. Now, again, you could have alternatively converted that to the pKb and subtract 14 from it to get to the pKa, which I think if you did, you might end up with 9.26 or something like that, depending on rounding. So there are a few different ways, obviously, you could get to the pKa value. This is really, as we will see shortly, a sort of basic buffer here. And since we do have a KB and it's a basic buffer because we were using a weak base, we could also have used the POH version of the Henderson-Hausbach equation if we wanted to with the pKb value. And again, just subtract 14 at the end of that to get to the pH. So there are a few different ways that you could kind of get to the pH on this one. So here I'm just going to go into the Henderson-Hausbach because I do just want the pH. So just go right into here with the appropriate things, and that's going to get us a 9.25 plus the log. Once again, our base is the NH3, which is ammonia, which is a weak base. And this is our acid here. So we want to go base over acid. So 0.3 over 0.36. Once again, our buffer components is NH3 and really NH4 plus. This is really the active really parts of the buffer in this case. This obviously being our weak base and is conjugate acid in this case. Again, as we talked about, the acid should have one more H plus than the base, right? So it's able to give it away if it needs to. And again, that's the way you can recognize it. So popping that in, it's going to get us an opening pH of our buffer here of error. No, that's not the same, right? 0.3 minus 0.36. A log, a little adding, couple more buttons. 9.17. We're going to open up here with our pH. Any questions on that? Again, as I mentioned a second ago, because we haven't added anything to this and we have the concentration both of the acid part of the buffer and the base part of the buffer, we don't have to worry about converting to moles or anything like that. Again, we can go straight on into our equation. All right, then let us do the second part here where we are going to add to 80 milliliters of this buffer 20 mils of 0.05 molar sodium hydroxide. So we just copy over some stuff here. So we got 0.3 NH3, 0.36 molar ammonium chloride. We have a pKa still of 9.25. And now we're going to add 20 milliliters of 0.05, I think it was 0.05 molar sodium hydroxide. All right, so clearly here we have our buffer and we have 80 milliliters of our buffer. So we have our buffers in there, and then we're going to add obviously the sodium hydroxide to it. So this again is a nice table situation that we need. And we do need to do things in moles. So you might want the moles of everybody here. So the moles of NH3. Again, we have 80 milliliters of our buffer. So that's going to be 0.08 liters as we convert it to liters. We're going to times it by the molarity of the NH3, which is 0.3 moles per liter. And that's going to get us here 0.08 times 0.3. 0.024 moles of NH3. We'll do the same thing for our ammonium and 0.08 liters. Again, the buffer, both components of the buffer will have the same volume since, frankly, they're in the same beaker, right? So they have the exact same volume. So we're going to times it by 0.36 moles per liter. Going to get us here 0.0288 moles of NH4Cl. And lastly, our moles of our sodium hydroxide. We have only 20 milliliters. Again, got to convert it to liters, times it by the molarity 0.05 moles per liter. Looks like 0.001 moles of sodium hydroxide. Any questions on that calculation so far? All right, so when I react or toss my sodium hydroxide into my buffer here, which at this point has some NH3 floating around. It's got a little NH4 plus floating around. The sodium hydroxide, which is a base, will react with what thing here? It's going to react with the acid part of the buffer, right? So again, giving us that acid-base reaction that's going to occur. So it's going to react with the ammonium chloride, and if you want to keep the chloride in there, you can. If you want to take it out, you don't have to. It is going to send an H plus this way, which will always form, as we've talked about, the other side of your buffer, which is NH3. You'll also get some water, and dare I say a 3-pack here. You'll also get a little sodium chloride action, kind of floating around freely as like a spectator ion basically floating around. Now we're going to do our ice table here. We're going to go initially here, our sodium hydroxide 0.001. Here we do have our NH4, which is 0.0288. Remember, it is not a buffer if we don't put an initial over here on the right-hand side, right? 0.024. And obviously, don't have to worry about the water. Do I really have to worry about the sodium chloride in this particular case? I don't. Again, it's a neutral salt, so, it is there, but it's not going to really do anything. So we don't really have to put any numbers. Once again here, when we do this ice table on moles, we do know what the change should be. And again, in this case, should be the smaller case, which in this case will be our sodium hydroxide. So that's going to be the change that's going to occur. And we're going to add it over here. And that means at equilibrium here, we will have nothing of our sodium hydroxide because, of course, we made a very good buffer, hopefully 0.001. We're going to end up with 0.0248 moles of our ammonium chloride. And remember, on the right-hand side here, it is adding, not subtracting, which again is a common error people make, 0.025 moles. Any questions on the ice table here? We can now look for our total volume, which obviously we had 80 milliliters of our base buffer, and we added 20 milliliters of our base. That's going to give us a grand total of 100 milliliters as our total volume. That is what we're going to convert everybody back into molarity by dividing it by the liters, which would be 0.1 liters if you converted 100 milliliters into liters. That's going to get us here 0.25 molar and 0.248 molar there. 0.248 molar. Any questions so far? Well, let me see what I did there. Point 0288, right? And we are subtracting 0.001, 0.0278. Yeah, yeah. Not a better day with the adding today. There, we got close. Or subtracting. That's okay. Was it here the other day? I did 1 + 1 didn't equal 2. Math really wasn't my thing, I suppose. All right. All right. So then obviously we're going to be looking at 0.278. Thank you. So now that we have it, again, if you're not sure what's going on, we can use our ice table to help us. And again, we still have obviously our buffer still happening here. And because this is still a buffer, we can go into our Henderson-Hasselbalch. And again, it's going to be the same pKa value, 9.25 plus the log. Once again, we want to make sure we get our base up there on top, 0.25 divided by 0.278. And that's going to get us here. That's going to give us a pH of 9.20. Again, you could have done an ice table at the end of this. And like I said, you do have a variety of options after this one. You could do a KB ice table if you like. You could do a Ka one with the NH4 plus, or you could just go to Henderson-Hasselbalch with the right numbers. Perhaps get it. Does make sense, right? We started with a buffer at 9.17. We added some base. We did not jump too high, right? So pretty good there. And it did go in the correct direction. The pH did go up again because we're adding base. So if you calculate and you got less than what you started with, you're definitely going in the wrong direction. Questions on that one there. All right, then we're basically going to take the same buffer now, and we're going to add some HCl, and I went with 2 milliliters of 6 molar. So we're going to go now, call this part C, 2 milliliters of 6 molar HCl added to our 80 milliliter buffer from previous one. So I'm just going to steal some numbers. Obviously, we already calculated the moles of each of our buffer components, and they're going to be the same, obviously, to start with, so we won't recalculate it. So we'll just get the moles of the HCl, and that's going to be 0.002, I think, times our 6 molar. And that will get you here 0.012 moles of HCl. Now, when we add our HCl to this buffer, it is going to react with the base part of the buffer, which in this case is the ammonia, right? NH3. And that is going to create us NH4 plus and Cl minus. Again, you could actually keep it together if you want and just call it NH4Cl on the other side, or you could break it apart, whichever way you want to do it. Again, the major part that is the buffer is this guy, obviously, and this guy. So in this case, it's your call. I'm just going to leave it separated in this case. And the reason for that is it's chloride, right? Which is also neutral, right? So I don't have to worry about it. So I can just kind of throw it to the side and not have to worry about it. All right. So using our moles here, which again, we're adding volume, we just got 0.012 moles. We have our moles from the previous step there. So I'm just going to steal them there. 0.024 for this one, 0.024. And also, again, to make sure it is a buffer, we got the NH4 plus 0.0288. Once again, here, the change is going to be the HCl, which is the smaller number. Grab a little bit more concentrated acid in this case. And that's going to give us here 0. See if we could redeem my calculator move here. Minus 0.012. That's going to give us 0.012 moles here and 0.0288 plus 0.012, 0.0408 mole. Any questions on the table so far? Our total volume this time around, though, is we had 80 mils of our buffer. We added 2 mils of our acid. That gives us 82 milliliters as our total volume. So we're going to divide this by 0.082 liters, again, converting that into liters from milliliters. And that's going to get us here, my made up one. We'll see how we did. We're going to end up with 0.1463 molar for NH3. And 0.49756 molar. Once again, still a buffer, so we could go into our Henderson-Hasselbalch, still the same pKa, 9.25, plus the log of my base, which once again is here, 0.1463, divided by our acid, 0.49756. And if we do that there, we can go 0.1463. Divided by 0.45756. And we're going to log it. And we're going to add 9.25 to it. Going to get us a pH of 8.75 in this case. Yeah. Again, we started with the buffer at a pH of 9.17. Here we added acid. It went down. Not too bad. A little bit bigger of a change because we did add 6 molar acid in this case versus the other way where we did 0.05. And this is only 2 milliliters of it versus 20 what we added in the last one. So here again, drop it. It didn't drop all the way down there, and it did go in the acidic range. Any question on buffer calculations either way? Yes. And just like on the previous step, if you wanted to, you could have ice tabled it up instead of the pH or penetration spot. Question on buffers? Buffers aficionados? All right. All right, then we're off to the next, before we zoom in. All right, let's zoom. We're off to the next big topic of the season here, and dare I say, almost the last topic here, chapter 14. Sadly. It is titrations, everybody's favorite thing. Yes. Go until you see pink, right? And then keep going. Don't worry about it. Dark pink is good. All right, so we're going to do titrations, and titrations is the process where, typically speaking, we have one solution we know everything about, so sort of like a known solution. We know the molarity of it or the concentration of it. We know how much we use of it. And then we usually have some type of unknown solution where maybe we don't know the molarity of it, something about it we just don't know. And we usually add, obviously, through a burette, right? And we do a titration here. And we typically will do this titration to help us understand something about the unknown solution. So through the titration, we can use something like stoichiometry to figure out something like the concentration of the unknown acid. You could also figure out something like its equivalent mass or molar mass. You guys do that in 50 still, like equivalent masses? Equivalent masses still? Wow, that's old school. And we could do some type of calculation to do so. Where do we usually stop a titration in a normal titration? We do usually stop it at what is known as the equivalence point. And the equivalence point in an acid-base titration is the point where exactly the moles of the acid equals the moles of the base. So in an acid-base titration, once you reach the equivalence point, that is the exact point where you basically have used up everything you started with. So you've added enough moles of base to use up all the acid or vice versa, and you have none of that left over. The equivalence point shouldn't be confused with the endpoint of a titration, which is sometimes referred to. The endpoint of the titration is where you lay up your titration, you stop. And hopefully, if you do a good titration, your endpoint is near your equivalence point. If you do a bad titration, maybe not so much. How do we know when to stop? Well, we use an indicator, yes. And we use an indicator, which is usually added to the solution. And it usually will change color around the equivalence point is where you want it. And that's a visual representation of, I should maybe stop titrating at this point, right? Everybody's favorite indicator is our friend, a little phenolphthalein. Bonus spelling later, right? Secret word, spell that correctly next time. So phenolphthalein is an indicator that is used, right? And is what color in acidic solution? It is colorless, yes. And neutral solution, it is still colorless, by the way. And a basic solution, it is pink. Yes, that's the only choice left on that one, yeah. And so we'll talk a little bit more about indicators as we go through the chapter, but pretty much indicators are weak acids in a lot of cases. And how indicators work is they work over a specific pH range. And for example, phenolphthalein works at a pH of 8.3 to like a pH of 10. At around 8.3, it is still colorless. As you start gradually moving in this direction, you get lovely shades of pink to fuchsia to super dark pink as you could get it as you keep moving down towards a pH of 10. Perhaps some of you remember seeing some of those colors as you were titrating, maybe in the last class. Now, where they always yell at you, right, when you do a titration, which is you need to stop when you see the very first faint sight of pink appears, right? It stays. And the reason for that is if you do that, you're probably back in this area, which is probably where your equivalence point is. And your equivalence point is probably in the colorless range of the pH. But as soon as you get the light shade of pink, that means you just got past it. And you're probably pretty close to your equivalence point. So that's why you want the lightest shade of pink. Now, we will answer the questions that everybody says, or the thing that everybody says when you titrate it. In fact, when you do titrations, you might have said this exact same phrase when you were titrating, which is, I only added 1 drop and it went like super dark pink. There was like no color a second ago, and now I added 1 drop and it's super dark pink. Then your teacher said, well, that's kind of pink, too pink. Maybe you should retitrate. Anyone? Did teacher say that to you? Oh, your teacher told you that. We'll see why you didn't really probably have to do that. Waste your time. So, but there's a reason why they tell you that. But in reality, you probably didn't need to do that. So we'll explain that and what's happening and why that actually occurs to end that mystery. As we use a burette, as you also know, right, it does increase when you take volume readings, right? So as you read down, you're taking the volume starting to increase. So if you are somewhere in this range, it's actually 1.5 milliliters rather than 2.5, right? So it increases as you go down. And when you do a titration, right, there's always 2 really important readings, the initial and the final, right? So you always want the initial and the final so you know how much that you added. That's not too bad of a titration, right? I find that most people get really dark pink until you say 2 magic words, extra and credit. And then all of a sudden everybody knows how to lightly get the lightest color of pink known to man. I learned that the hard way. Everybody starts shoving flasks in your face. Is this light enough for the extra credit? I said, if you take the flask out of my face, maybe. All right, so let's talk about titrations here and what's going on. We're going to talk about a few different types of titration. So the first type of titration we're going to actually talk about is a strong acid and a strong base titration. So this is like a titration if you took some like hydrochloric acid and you reacted with some sodium hydroxide and you get a little acid base reaction where of course you make a salt, which is sodium chloride in this case, and water, right, which is H2O, right? Now, for orientation purposes, what's happening here is up in the burette, you have your sodium hydroxide, and down in your beaker or your flask, you have your HCl. So we're adding sodium hydroxide to the HCl. When we do that, that creates what we see here on this graph, which is pH versus volume of sodium hydroxide added. This is what is referred to as a titration curve. It's our friendly neighborhood titration curve. And we could see that we're starting at a low pH because we're starting with an acid, and we're eventually ending up at a high pH because we're adding base to it, right? So this gives us our entire sort of section. Now, when we look at a titration curve such as this, there's actually 4 different parts to the titration curve. Part number 1 is actually over here where I kind of circled. That's the first part. And that's really before you start the actual titration. So before you add anything, like in this case, before you add any sodium hydroxide, that's sort of the first part of the titration curve. The second part of the titration curve is once you start the first drop, all the way to before the equivalence point, that is sort of your second part of the titration curve. Then you hit the equivalence point. That is definitely your third part of the titration curve. The good thing about us, as we will start titration shortly, we just keep going. We don't care about that equivalence point and any type of pink color that we see. We just keep going. And that is after the equivalence point, which is all the way through here. So these are the 4 different sort of areas of a titration curve. And you will be able to calculate the pH anywhere along this titration curve. So let's talk about how we can calculate the pH here. So let's start with our first part of this titration curve, which is before we begin. And obviously here, before we start the titration, really, we haven't added any sodium hydroxide in this case. Pretty much the only thing sitting in my beaker or flask is a little HCl, right? And HCl is what type of acid? That is a strong acid, which means in reality, my little beaker is H plus is floating around, right? And Cl minus is floating around since it is a strong acid. That means at this point, if I want the pH of it, what do? pH of a strong acid, you could just go right into the pH equation, right? Because you will know the concentration of your HCl in this example, and that is the same as the H plus concentration. And you can really go right into the pH equation there and actually figure out what the opening pH of that is. We have not added any volume at this point, which means we don't have to worry about moles or anything like that. We can use the whole concentration of it, whatever it is, as we poured it into our beaker. Questions on that? All right, then let's talk about what happens next. We're going to hit the second part here, which is we're going to start our titration. So we're going to add some sodium hydroxide here. And we're going to take it all the way from like the first drop to right before the equivalence point there. And this is going to be before the equivalence point. So before the equivalence point, because you're obviously adding sodium hydroxide in this case, you will actually need an ice table to figure out what is going to go on. And you are going to get a reaction. And the reaction you're going to get is what we just were talking about. You're going to have your sodium hydroxide reacting with your hydrochloric acid. And again, going to make our salt there and water, right? By the way, here I'm adding sodium hydroxide to my HCl. This ice table should be done in molarity or moles. What happens when I add volume? I should do the ice table in moles. And that's all through a titration, right? You're doing nothing but continuously adding volume, right? So your molarity is changing throughout the entire titration. So the opening ice table that you will have to do in any titration calculation should be done in moles because, again, you're adding volume there. Just like we did with buffers, when you're done with that very first table, you should convert back to molarity and using the total volume. So the total volume in this case, obviously, would be how much of the acid you started with and how much of the base you dropped in, right? Wherever you're stopping at that point. So here we're going to do this ice table in moles. And just so we're clear and just so you understand when you look at it later, I am absolutely positively making these numbers up. Yes, so that's where I got them from. I just made them up. So we are starting with this in my beaker, and I am adding this to my beaker. So I'm going to say we're starting with the lovely number of 4 moles of HCl. Now, if I am before the equivalence point, should the moles of what I'm adding be less than, equal to, or greater than the moles of my HCl in this case? They should be less, right? Because I know if I'm at the equivalence point, which I am not there yet, they are equal, right? So before I get there, what I'm adding has got to work its way up there, right? So it's got to be less. Then obviously, if I go past the equivalence point, it's now got to be more than what I started with, right? So that's the thing we want to think about. So again, just making up this number, it is a 2. Seems like a nice number. Although I did have trouble with 1 plus 1, so maybe we'll be in trouble here as well. So we're going to go over here. We're going to go 0. Once again, at this point, and typically when we do an ice table, just like we saw with buffers when we're doing with moles, we actually know what the change is. And at this point, it is always the smaller number. And really at this point, our sodium hydroxide here is like the limiting reagent. We don't have enough. And like the HCl is like the excess reagent basically in this situation. And that means that the change here is going to be my smaller number, which is -2, and a +2. And that means at the end here, we will end up with 0 or -2. I'm going to try without the calculator, 2 moles, and 0 plus 2. That's going to go with 2 as well. My math teacher would be very proud. All right. At this point, like I said, definitely in the sort of titration calculations, good idea to convert ourselves back into molarity. So as I mentioned before, we would at this point figure out how much of the acid we started with, how much of the base we added from the burette we added in there, and we would convert these guys back into molarity, again, dividing by our total volume. Yeah. That's been converted into liters, obviously. All right, so at this point, if we take a look at our ice table, we got a couple of things left over. We got some sodium chloride, we got some HCl. Is that like a buffer, by the way? That is not a buffer, right? Because HCl is a strong acid, and you cannot have a buffer that is a strong acid. So earlier, you remember when we were talking about our friend the Henderson-Hasselbalch equation, I said that when you end up with two numbers, people like to throw them in there. This is very common where this happens because they're like, cool, two numbers. I'm going to toss it in there because it seems good. So this is, again, not a buffer situation. We have two things really at this point. We have a salt and we do have a strong acid. So earlier we talked about the sodium chloride. That's what type of salt? That is a neutral salt, which means we don't really have to worry about it, right? And really what we're left with now is a strong acid. And we now have the concentration of that strong acid. And that is the H plus concentration. And that means that you can now go into your pH formula minus the log of the H plus. So in this type of titration, you have to do one ice table anywhere from the first drop to before the equivalence point. And the purpose of the ice table really is to figure out how much of your strong acid you got left over at this point, basically, how much of it you used up. And once you have the new concentration of it, you could go right into the pH equation again because it's a strong acid, and that will be your H plus concentration. Any questions on that there? All right. And that is pretty much all the way through from, like I said, the first drop to the equivalence point. That is what you need to do here. And obviously, you're going to start to see your H plus concentration from your strong acid start to go down, right? Because we're using it up. And as we see that, we start to see a rise in the pH, right? As we're moving towards the equivalence point, because we're now using up more and more of the H plus, which means we have less H plus, more OH minus, and the pH starts to rise, right? So we're starting to see a rise in our sort of titration curve here. So now we come to the equivalence point, which is the next part. And this is typically what you see when you look at a titration is as you're approaching the equivalence point here, I'll try that one. We usually have a pretty good rise in the pH to the equivalence point. And by the way, you will typically have a pretty good rise after the equivalence point uh, to where it starts to level off. And we're going to reach the equivalence point at this point. Now, this is the reason why people say that saying of I added one drop and my color went crazy, right? It went dark pink. That is because as we approach the equivalence point, kind of like from here to here and even past the equivalence point, it goes pretty vertical, right? And because it goes pretty vertical, am I changing the volume a lot at this point? If I just go straight up at this point. No, you could pretty much pick anywhere along this line, right? And you're going to pretty much hit the same volume, right? But what does change a lot is the pH changes greatly as you go vertical, right? So what happens is you do not need a lot of volume to change the pH a lot. So why does that make your thing turn super dark pink that everybody likes? That is because, again, phenolphthalein works on a pH range of like 8.3 to 10, colorless over here, super dark pink over here, and so forth. So when you add one drop, you may actually be way up here, right? In your pH, because you're going to change the pH a lot by adding one drop. And now your indicator, because you're now at like a pH close to 10, is going to be super dark pink, even though a minute ago you were down here and you're like colorless at that point, right? And so just adding that one drop, you do not need a lot of volume as you reach the equivalence point or near the equivalence point to change the pH a lot. And what that does for your indicator is it changes the color of your indicator a lot, even with a very, very small volume. Any questions on that? So that's why you will see that and why they tell you, hey, try like half a drop and dilute it down so you're not adding as much of a concentrated drop there, and that'll kind of keep it from maybe becoming really dark. Now, why do they tell you to redo your titration? Where if you were really careful, and you maybe missed it by a drop or even two drops, and maybe you're even up here, is your volume when you're here are really at the equivalence point all that different? It is not. Again, you can take anywhere there, and you're pretty much at the same volume, which in the like the titrations you did in Chem 50, that's all you cared about was like the volume of the equivalence point, right? So you could figure out everything. And then most times you are not. But the reason is they tell you a lot of times, or sometimes teachers will tell you, well, that's too dark. You need to go redo it. Is because if you titrated like I did when I was in school, I was always the first one done because I just opened that thing up and just let it all drop and close. They go, you said pink, pink it is, right? So if you weren't really careful, you titrated really crappily like I did, I could be like way over here, right? And my pink color is going to be like the same color it is like over here, right? And now am I close to the equivalence point? I am definitely not close to the equivalence point, right? I'm very, really far away. So in reality, if you were really careful as you were titrating, you just missed it by a drop or two. There really was no need for you to redo it because you probably would have the same volume regardless. But if you weren't careful, you could find yourself really, really far away from the equivalence point. And that's why usually teachers used to yell at people to go do it again. Any questions on that? Mystery solved, perhaps. I don't know. Yes. All right. All right. Let's talk about really what is happening, though, when we do reach the equivalence point. So let's come back here to step number 3 or step part 3, which is at the equivalence point. So let's take a look at what's happening at the equivalence point here. Actually, let's kind of go through here. So at the equivalence point, we obviously are still having a reaction occur. So again, we'll have, however we want to write it, HCl plus our sodium hydroxide. Again, going to have the same reaction occurring here, sodium chloride and some water. And again, this is what we're starting with. This is what we're adding. And if we do our initial made up number of 4 moles, how many moles of sodium hydroxide should I have at this point? If I'm at the equivalence point, it should be 4 because that's basically the definition of the equivalence point is equal moles, right? So I will say in some titration problems, they may not tell you the volume you need to get there. They may just say, what is the pH at the equivalence point? So there are a few different ways you can figure out the volume because you will need the volume to figure out the total volume so you get to the molarity at the end, right? So if you are not given the volume to reach the equivalence point, and it is a one-to-one relationship between the acid and the base, you could use our good friend, the titration, our dilution formula, M1 V1 equals M2 V2. Again, it's got to be a one-to-one relationship to do that, which most of the ones you come across are. If you not sure you should use that, you could just use the definition of molarity, right? Which is molarity is moles per liter. You will know the molarity of like the base you're adding, and you'll know because you're at the equivalence point, like somebody just answered a second ago, the moles that you should have, it should be equal to these moles. That means you could just rearrange and solve for the volume that you would need, and will get you how much volume to reach the equivalence point. So there are a couple of different ways to do it, and sometimes you do have to do that. Like I said, there are a number of titration problems where they just simply go, "Hey, what is it at the equivalence point?" They won't tell you how much you actually added to get yourself there. Any questions on that? All right, so 0. Good news on this deal at the equivalence point is you hopefully can't pick the wrong number because there's only one number to choose, which is 4 in this case. And we see here, as we expect at the equivalence point, we got nothing left there, nothing left there. And we got some 4 moles over here, which again, using our total volume, amount of acid we started with, amount of base we added, convert it back into molarity. Any questions on that ice table there? At this point, we got just sodium chloride left. And sodium chloride is what type of salts again? Which means the pH at the equivalence point should be 7. No calculation needed because the only thing you got left at this point is a neutral salt that will not go through hydrolysis. And you got some water, which is all should be neutral stuff. So in this type of titration of a strong acid and strong base, and specifically only titration of strong acid and strong base, we should have a pH around 7 at our equivalence point. And if we take a look at the little graph here, that is what we see here. We got about a pH of 7 right there at the equivalence point. And again, we basically just have a neutral solid and water basically present. Any questions on that there? All right. Like I said before, it turns pink at this point. It doesn't stop you. So you decide, hey, again, we'll just shoot past there. And now we're going to look at what happens once we get past the equivalence point. And typically in our class, we have titrations with no regrets here because we go all the way past the equivalence point and we want the entire titration curve. So it's good news. You can keep going. So let's see what happens here and how we kind of get to our pH after the equivalence point. So we're now going to be after the equivalence point. And again, we still have a reaction that's occurring between our acid and our base. And again, we're starting with this. We are adding this. And I'm going to start with my made up number of 4 moles again. Now, when I get to the sodium hydroxide moles and I'm past the equivalence point, should I have less than, equal to, or greater amount of moles of sodium hydroxide in this case, since I'm adding it? I should have greater, right? Again, we're equal at the equivalence point, and if we keep adding, now whatever we're adding is going to be greater than what we started with. So again, just making up a number here. I'm going to go with 6 moles. Yeah, seems like a nice number, maybe. We'll see. And a 0. Now what happens as we go past the equivalence point is there's actually a change that occurs here. We now do not have enough of HCl, or the acid, and our acid becomes like our limiting reagent. We have plenty of that sodium hydroxide because, frankly, you did not stop titrating. You just let that thing drip in there and keep going, right? So you got plenty of it coming in. And that's important for the change. The change in this case will now be the acid, right? Again, the smaller numbers, you don't get a negative number. -4, -4, and a +4 here. That's going to get me here zilch for my HCl, 2 moles for my sodium hydroxide, 4 moles for my sodium chloride. Again, dividing by the total volume converted to liters will convert both of these guys back into molarity. So again, if you're not sure what's going on, you can look at your ice table and kind of see what you got going on. So we got some sodium hydroxide and sodium chloride left over. Is this a buffer? Again, not a buffer, even though you got 2 numbers, right? So as we've been talking about, obviously this is a neutral salt, so we don't really have to worry too much about that. But we do have this guy, which is actually a strong base, right? Hence why your pH skyrockets after the equivalence point, right? Because at the equivalence point, you used up all your acid, and that didn't stop you. So now all you're basically doing is just dumping in there hydroxide, right? And that's going to make the hydroxide concentration go really high, and that's going to make the pH go really high. And again, that's why we kind of see a jump after the equivalence point as well as we get there. So because of that, this concentration here is actually your hydroxide concentration in most cases, since that is your strong base. That means that you cannot directly get the pH, but you can go pOH first and then subtract 14 to get you to the pH in this case. So past the equivalence point, anywhere past the equivalence point, you do need to do 1 ice table in moles. The whole purpose of that ice table is to figure out how much strong base you just dumped in there and you have left over. Once you have the concentration of your strong base, you can get the pOH and then get yourself to the pH. Any questions on any parts there? No. So those again are the 4 parts, and you want to make sure you're able to calculate the pH anywhere along there. So why don't we try one? Let's just do, I don't know, let's do this one. What is the pH after you add 23 milliliters of 0.1 molar sodium hydroxide to 25 milliliters, I think, of 0.1 molar HCl in a titration? So again, same setup of titration. We're adding sodium hydroxide to the HCl. We're looking for what Okay, let's take a look. So this setup is the same setup. So again, we have our sodium hydroxide up in the burette, and we are adding it to our HCl here. And we're going to get a reaction, obviously, that's going to occur with our HCl, sodium hydroxide, and going to make some sodium chloride and some water in this case. Once again, here we are starting with this. We are adding this, and we are going to do it in moles. So we're going to convert each into moles. So initially here, our HCl, we got 0.0025 moles. Again, convert our milliliters into liters, times it by the molarity. For our sodium hydroxide here, we got 0.0023 moles. We got 0. First off, any questions on that there? Question I have is, am I before, am I at, or am I after the equivalence point at this point? Where am I in my titration? And before the equivalence point. You could always figure that out by looking at your ice table. If the moles of what you're adding is less than what you are starting with, then you are before the equivalence point. If they are equal to each other, you're at the equivalence point. And again, if the moles of whatever you're adding is more than what you started with, then you are definitely past the equivalence point. So why is that important? It is important for some of the other titrations we're going to talk about, because if you kind of know where you are in the titration curve, you can, before you even kind of do the calculation, kind of know what type of calculation you should be doing. So sometimes it makes it easier to kind of do the calculation part. All right, so since I'm before the equivalence point here, obviously I do not have enough moles of sodium hydroxide. That's going to be kind of like our limiting reagent deal, and that's going to be the change we're going to use here. Also, it is the smaller number, right? That means when I do reach equilibrium here, we will have 0.0025 minus 0.0023. 0.0002 moles. We got nothing of sodium hydroxide, and 0.0023 moles of the sodium chloride. Once again, here, we just want to make sure we convert back into molarity here. And to do that, we need a total volume. So we got 25 milliliters we started with. We just added 23 milliliters to it. I'm going to go no calculator here, 48 milliliters. So we're going to divide each of these by 0.048 liters, which is converting that milliliters into liters by dividing by 1,000. That's going to get us here 0.048, I think. We're going to end up with 0.00416 in this case. And we'll do the same thing on the other side, 0.0023 divided by 0.048, 0.0479 molar. Any questions so far? Once again, looking at what we got left over, sodium chloride and HCl. Once again, although they are related to each other, it is not a buffer. Still have our neutral salt. So what we really have left over is our strong acid. And because of that, that means that this will be our H plus concentration. And that means we can now go into our pH minus the log of 0.00416 and minus the log there. 2.38 pH. That's good. Any questions on that there? Let's see how we did. This is actually this titration, I think. So 23 puts us right around these two in between. So 2.38 is higher than that one, less than the next one. So did all right, I guess, on that. Yeah, it's not too bad. Any questions on strong acids, strong base titration? Yeah. All right, the next type of titration we're going to do is the one you're familiar with, I think, is a titration of a weak acid with a strong base. And we'll use acetic acid here, which is probably the titration you did in 50, plus some sodium hydroxide, which is our strong base. Again, we're going to get a double displacement reaction that's going to happen here, and we will end up with some sodium acetate on the double exchange and some water, right? So basically going this way and going this way, right? Exchange. All right, so the setup here is very similar to the last one. Up in the burette, we still have this sodium hydroxide, and down in the flask or beaker, you have your acid. So again, we're adding base to acid in this case as we're titrating. That is why we also see a similar S curve as we saw in the previous one, where we're starting at a low pH and then in at a high pH because we're adding base along the way. We also see we're starting a little bit higher here than we are maybe on the previous one in terms of the pH, and that's also because the previous one was a strong acid versus this one, which is a weak acid, right? So just by definition of a weak acid, it's not going to release as much H plus as say a strong acid. So you might actually be starting with a little bit higher of a pH. There is still on this titration curve the exact same 4 spots. So we have kind of again spot 1 before we begin, after we begin, before the equivalence point, part 2, part 3, the equivalence point, and then obviously here past the equivalence point is going to be our 4th part. So once again here, we're going to kind of look at each of these and understand hopefully the calculations to go along with it. So we will start with our first step here, which is before we start the titration. And before we start titration, once again, what we have in our beaker or our flask, in this particular example, is acetic acid. And acetic acid is a weak acid, which means if I want the pH of a weak acid, what do I need to do? Put it in your beverage to keep it cold. Like an ice table seems like a good thing, right? So this is going to be just a basic Ka type problem like we did earlier on in the chapter, a weak acid type problem. Our weak acid is going to dissociate into H plus and some acetate here. You will also have the Ka value for acetic acid, 1.8 times 10 to the minus 5, perhaps. And this will be an initial tier. And because we have not really started our titration, we have not added any sodium hydroxide to it, we have not changed the volume, which means we could just use the molarity, the initial molarity of the acid. We're good to go. So this is going to be a molarity table with zeros and X's. Yes. Our normal sort of ice table here, Ka type of situation. Just like normal, right? We would then go into our Ka expression. We would then solve for X. And X in this case does equal the H plus concentration, as you can see. And obviously at that point, we can then go into our pH formula here to calculate. So a little different than the last one where we had a strong acid, we could just go right into the pH equation. Again, because this is a weak acid, it's going to set up that equilibrium, which does require us to do an ice table to open it up out here and figure out the pH. Any questions on that? Obviously, you could solve this like any other ice table we've done previously. You could make the assumption, make sure you check it. It may not work in all cases. You could also quadratic it. You probably won't come across too many perfect squares and these type of problems. So it'll probably be one of those couple of ways of doing it. Any questions on that there? So opening up here in this titration, really just a Ka type problem. Now we're going to actually start our titration. And obviously here, that's going to take us before the equivalence point. So we're going to go before equivalence point. And obviously, we're going to get a reaction between the weak acid and the strong base. So we'll have some acetic acid here, which is our weak acid, reacting with sodium hydroxide, which is our strong base. And again, going to do a double displacement reaction that's going to occur here. We're going to switch partners, right? And when we do so, we will end up with sodium acetate on that double exchange and some water in this case. So once again here, this is what we're starting with. This is what we are adding. And since we are adding sodium hydroxide in this case, should I do this ice table here in moles or molarity? It does need to be in moles, and pretty safe bet usually first ice table off of a titration problem should be in moles. So we're going to do that. And again, I'm going to make up my number here. So I'm going to start with my same 4 moles here, my weak acid in this case. And much like we talked about on the previous one, since I am before the equivalence point, the moles of the sodium hydroxide I'm adding should be less than what I have there, right? Because I haven't got the equal yet. So again, I'm going to make up the number of 2 and 0. At this point, this sodium hydroxide is the limiting reagent, as we do not have enough to react with all of my excess reagent at this point. So the change here is going to be our smaller number, which is our 2 moles in this case. And that means at equilibrium, I'm going to have 2 moles of acetic acid, 0, and 2 moles of sodium acetate. Again, just good practice. At this point, using the total volume, I'm going to convert everybody back into molarity. So we're going to divide by our total volume again and convert everybody back into molarity. At this point, if we take a look at our ice table, we have sodium acetate left over. We have acetic acid left over. What do I have left over at this point? Are those two things related to each other? That's acetic acid and sodium acetate. They are related? I'm going to say they are related. That to me seems like a weak acid and its friend, the conjugate base, also known as a buffer. Yeah. So you actually just created a buffer at this point in your titration. Congratulations. Good job. Right there. We made a buffer. So if you remember when we were talking about buffers, by the way, we were talking about the idea that you can create a buffer from a reaction of like a weak acid and a strong base, or a strong acid and a weak base. And that is what happens here in the titration. So as you're doing this titration, you're actually going to make a buffer, and then you're going to subsequently blow through your buffer as you continue to add your sodium hydroxide. Because as you continuously add your sodium hydroxide, you will blow through your buffer until the point where it is no longer a buffer. And you'll see that big jump in pH to the equivalence point, right? So you kind of blow through the buffer and you're going to see that jump here. Now, because this is a buffer, that means if I want the pH, I can go right into the Henderson-Hasselbalch equation at this point. And obviously the pKa value would be coming from the Ka value of my weak acid, right, in this particular case. That would be given to me probably in the problem. So before the equivalence point, you will always create an acidic buffer that you can figure out the pH one of 2 ways, like we show here. You need a minimum do 1 ice table. The purpose of that ice table is to figure out the molarity of your buffer components. And you could then follow that up with the Henderson-Hasselbalch equation. Alternatively, you could do 2 ice tables. First ice table exactly like that one to get the molarity of your buffer components. Second ice table is like the ice table you would do if you didn't want to use the Henderson-Hasselbalch equation. And again, you would have an initial concentration on both sides and do your X's and solve for X and all that kind of stuff. So as we go through this type of titration, create a buffer and then subsequently kind of blow through the buffer here along the way. So we get some buffering action that happens here. And like I said, as you get further towards the equivalence point, you start blowing through your buffer. And now you're going to get a pretty good jump there to the equivalence point in terms of its pH. Any questions on that there? All right, then let's talk a little bit about what happens here when we do reach the equivalence point in this type of titration. So if we get to the equivalence point in this type of titration, which is our third step here, we again are going to have a reaction that's going to occur. So we'll take a look at our acetic acid still reacting with our sodium hydroxide. And gonna make our sodium acetate and our water in this case, right? So once again, we will need an ice table here. It does need to be done in moles. So we'll go with our 4 moles that we started with here of our acid. This is obviously what we're adding. So if I'm at the equivalence point, again, the number of moles of my sodium hydroxide should be same number, right? So it should be 4 moles here and nothing going on. Once again, the good news at the equivalence point is can't pick the wrong number, hopefully. It's -4 in this case. -4 and plus 4 moles. That means when I reach the equivalence point here, I got nothing there, which is what I would expect to occur. I got 4 moles here. Once again, going to convert back into molarity by dividing by my total volume at this point, which once again is obviously how much acid you started with and how much base you added in this case. At this point, the only thing I got left at this point looks like a little sodium acetate. Sodium acetate is a, put it on your fries, salt. We'll just play game show here as we're going through the whole lecture. So it is a salt, right? So whenever we have a salt, the one thing we need to think about is, will that salt go through hydrolysis? So obviously my next question is, will this salt go through hydrolysis? It's a yes or no question. So that's a 50-50 shot. Do you want to double up your winning so far and go for the answer? So in order for it to go through hydrolysis, part of your salt needs to come from what type of thing? A weak acid or a weak base? Is there a weak acid here? I'm going to say yes right there, yeah? Which means this is a salt that comes from a weak acid, which means congratulations, your reward is it will now go through hydrolysis, which means once you reach the equivalence point, you don't get to just do one ice table, you get to do double the ice table because this part of your salt, just the acetate part, right? As the sodium part of your salt is still neutral, right? Not going to go through hydrolysis, but it is this part of the salt that will go through hydrolysis. And since it came from a weak acid, it will act as a base, right? When it goes through hydrolysis, and it's going to accept the H plus and make back my acetic acid here. And the result of that donation of the H plus from water, it will produce hydroxide. Yeah. Which means before I finish my calculation here, when I reach the equivalence point in this type of titration, should it be acidic, basic, or neutral? The equivalence point should be basic because you have this salt going through hydrolysis, and your equivalence point here is not going to be a pH of 7 like in the last titration, because here you will have a hydrolysis happening and it will be a basic pH, which is also quite important when you try to choose an indicator. You might want one that's a basic type indicator, which is why you probably have used in your life phenolphthalein, which works from 8.3 to 10, basic pH, right? Equivalence point should be basic here. And that's where you want your thing to choose and change color. You would not want an indicator, right, that would change color like at a pH of 4, because it's going to change way too early for you, right? You're not going to stop in the right situation. So how do we do this table? Well, the importance of converting back to molarity, as I mentioned a lot along the way, is really important here because you need the molarity of this guy to start with, and that is where you get it. Yeah, the equivalent point, the ending part of your first table becomes the initial concentration of your second table, and then this is going to be zeros. This is going to be minus X, plus X is like normal. This is going to be molarity minus X, X, and X. This is going to go into our K expression here, which is my acetic acid times my hydroxide divided by my acetate. By the way, that's a K what? B. Yeah, KB, because we do have hydroxide here. What K value do you think you probably were given in this problem? Yeah, you probably were given the Ka value for acetic acid. So this is a situation where you'll have to do the Kw, right? Divided by the Ka value will give you your Kb value. Do you have a question? Yeah. Why do we ignore water as a reactant and which one? The second reaction? We're not ignoring the water's actually sending the H plus over. But are you asking why we don't put any numbers there? Is that what you're asking? We don't because it's a liquid, right? So it's not part of the equilibrium. So much like up here as well, no sense putting numbers that you're going to use incorrectly right now. Yep. And the same idea as well. Sometimes, if you kind of identify maybe the salt's not going to do much, you may not want to use numbers. So we will have to use that relationship here to get ourselves to the KB, which is that KW divided by the KA. Also, quite important as well, when I do go through here and solve for X, what is my X actually equal in this case? Concentration of hydroxide, not H plus. Super common mistake. People think it's H plus always, right? So this is actually equal to the hydroxide, which means you're going to do a POH first, right? And then probably to the pH at that point. So again, these are things you want to think about. And obviously very different than the last titration where you just write pH 7, right? And you're happy, right? So this one, a little bit more work there at the equivalence point because we have a salt that's going to continue to react and go through hydrolysis. Any questions on that there? So to finish up this titration curve here, we're going to obviously go past the equivalence point at this point, and we're going to continue to add. So let's talk about what happens at that point. So once we go kind of past the equivalence point, we're still obviously adding, so we still have our same reaction that's occurring here. Get our sodium acetate and our water. And again, this is what we started with. This is what we're adding. So I'll use my made up 4 moles here. But now, because again, I am past the equivalence point, my moles of sodium hydroxide should now be more than what I started with, right? Because we're definitely past the equivalence point. So I'll use that 6 mole number I used previously, Na0. Again, at this point, just like we saw in the last titration, this guy is now going to become our limiting reagent. This is going to become our excess reagent, which means the change will be the smaller number here. And again, we're going to end up with nothing going on there. 2 moles over here and 4 moles over here. Like normal, we'll use our total volume, get these guys back into molarity at this point. So when we're done with this table here, we got sodium acetate left over. We have sodium hydroxide. Is this a buffer? I have 2 numbers. Can I use the Anderson-Hasselbalch equation? The answer is no, it is not a buffer. They are not even closely related to each other, right? Sodium hydroxide and sodium acetate. I have 2 things here. I have a salt, as we saw at the equivalence point, which will go through hydrolysis. And when it does go through hydrolysis, it acts as a base, right? I also have sodium hydroxide, which is so between these 2 bases, which one is stronger? The sodium hydroxide is a much stronger base than acetate in this case. Acetate's got to go find some water, right, to produce hydroxide. Sodium hydroxide just has to go for a swim, right? And it's going to break apart into OH minus, basically. So at this point in the titration, even though the acetate is still going to go through hydrolysis a little bit and contribute, the major contributor to the pH is the strong base. Because again, all it has to do is go in there and it's just going to make hydroxide right away. And because that's the major contributor and it is a strong base, that will give you your hydroxide concentration, which once again allows you to go to your POH and then to your pH in this case. So as you can see in this type of titration, which is a weak acid, strong base titration, very different than what you do in a strong acid, strong base titration. And again, because you have some salts here that will go through hydrolysis, you have some conjugate pairs that can make a buffer, right? So at the very beginning of the titration, you basically have a Ka problem. Second part of the titration here, you have a buffer problem. Third part, you have a hydrolysis problem. And last part, you have a strong base problem, right? These are all problems that we have done before. But what makes it a problem for people and a problem when they try to do it is they don't know where they're at and they don't know what they should be doing. So earlier I said it's a good idea to kind of think about where you are in the titration. So if you look at a problem like this and you go like, oh, cool, I'm before the equivalence point, I should be doing a buffer, right? Before you do the calculation problem. Or I'm past the equivalence point, I should be doing a strong base. Or in this case, I'm at the equivalence point, that's a hydrolysis problem. So sometimes it's good to take an extra second, think about where you're at, and think about what type of problem you should be doing. And you actually know what type of problem before you try to just to jump in there and try to figure out, what's going on. Any questions on that there?